Hello everyone, welcome back to another video. Today we're going to be looking at the grade 11 KZN 2024 paper. Specifically, we'll be focusing on the questions on electromagnetism. As always, if you'd like to give it a go, please pause the video. I'm going to go through the answers in 3, 2, 1. Question 1.5. The sketch below shows the magnetic field around a straight current-carrying conductor viewed from point X. Which one of the following correctly describes the direction of the conventional current through the conductor and the direction of the magnetic field lines? Okay, so let's start with the direction of the conventional current. So to get the direction of the conventional current, we need to look at the cells. This is the positive terminal. That is the negative terminal. Conventional current flows from the positive terminal to the negative terminal, meaning it's going to go in this direction. Let me just do it like this, like so. Okay, so if you are viewing it from point X, meaning you are looking downward, the conventional current is going to be moving upward toward you. Okay, so we have option C and option D. Next, let's look at the direction of the magnetic field. So remember, with electromagnetism, you are using the right-hand rule. So I've attached a picture here so you can imagine what it would look like. It is as if you are holding a can with your right hand or a cylinder with your right hand. So if you are holding it with your right hand and your thumb is pointing in the direction of the current, then your fingers, your other fingers, so from your index to your baby finger, these 4 fingers, the direction that they are curling is going to be the direction of the magnetic field. So in this case, it's exactly as the image shows. Your thumb is pointing upward and your fingers are going to curl like in the picture. If you are viewing it from the top, meaning if you are viewing it from X, your fingers are going to be curling in an anti-clockwise direction. Again, if you are viewing it from the top, your fingers are curling in an anti-clockwise direction. So the answer is D. Okay? Let's move on. Question 6. The apparatus shown below is used to demonstrate Faraday's law of electromagnetic induction. All right, so we have a magnet moving into a coil with an ammeter, and there's some current that is produced. State Faraday's law. We have access to this. These are definitions, so I won't go through them. State 2 ways in which the deflection on the ammeter can be increased. So this is a theory question. If you want to increase the reading on the ammeter or the deflection on the ammeter, the things that you can do is you need to increase the motion of the magnet or the coil relative to each other. So in other words, the faster you move the magnet through the coil, or the faster you move the coil through the magnet, the more deflection you're going to get. So move magnet through coil faster, or vice versa. Next, what you could do is you could use a stronger magnet. And the last one is if you have more loops. If you have more loops in the coil. or they call it turns, loops doesn't really matter. More loops or turns in the coil. Okay. Question 6.3, is X the north or south pole of the magnet? So what we need to look at is we need to look at these lines. See, they've drawn these lines for us, right? And we know from years past that if you have a magnet, you have the north end of the magnet and you have the south end of the magnet, and of course there are magnetic field lines around the magnet. Now the field lines go out of the north, so they point away from north, they point into the south. So you can see that these arrows are pointing away from the magnet, meaning that X must be north. Okay, so X is north. Question 6.4. Now this question was removed. So learners who wrote this paper, the marks were adjusted because there was an error in the paper. So let's try to figure out what the error was, or what the possible error could have been, and what we could do to make it possible to actually solve. So the question reads, the area of the circular end of the coil is 0.8 meters squared. The magnet is moved into the coil with its axis coinciding with the direction of the magnetic field as shown in the diagram. The magnetic flux, so this could be the point where there could have been an error here. The magnetic flux linked to the coil changes from 0.6 to 0.3 in 2 seconds. Now, why I'm saying that this could be an issue is because the magnet is moving into the coil. And if the magnet is moving into the coil, the flux should increase. That's what I'm saying. It could be a possible issue. Maybe this is why it was removed. So the flux should have increased. So it should have been 0.3 to 0.6. Then it could make the question could make it possible to solve in 2 seconds. Calculate the number of turns in the coil if an EMF of 7.5 volts is induced in the coil. Okay, so let's attempt it and see what answer we get. So remember, they want us to calculate the number of turns in the coil. In other words, they want us to solve for capital N. Now there's one equation that we know for capital N, and the equation is E, which is the EMF, is equal to minus N delta phi over delta T. Now let's go through the calculations, or let's go through the different things or quantities that we know. Okay, so we know that delta T, they tell us, is 2 seconds. Okay, then we can work out the delta phi. Remember, delta phi is equal to the final minus the initial. So remember, it went from 0.3 to 0.6. So 0.6 minus 0.3, and that gives us 0.3. And then we also know the E value of 7.5. Now we can substitute, or we can solve. We can say that E is equal to minus N. Actually, let's substitute one time. So 7.5 is equal to minus N Then delta phi we know as 0.3 divided by 2. Now if we solve for n, we're going to get an answer of negative 50. But we obviously can't be negative 50 tons. So in that case, we'll say therefore n is equal to 50. So there should be 50 tons. Now again, we're not sure why exactly this question was removed. We're not 100% certain, though even if you were to use these calculations as they were given to you, you should still get 50. Okay, again, this is just an example. There could be other reasons, but a similar question would be solved like this. Okay, so that's it for this paper. If you found it useful, please consider leaving a like or subscribing. If there's something specific you'd like me to do, then please let me know in the comment section below. Until the next one, bye-bye.